Have you ever seen an AI try to restore an old blurry photo and it just comes out looking, I don't know, weirdly smooth and kind of fake? Yeah, it's a super common problem, and there's a really fascinating reason why it happens. But what if I told you there's a totally new way to do this? An approach that doesn't just fix old photos, but actually lets us explore a bunch of different possible realities? Okay, let's dive in.
So let's just start with that big question right off the bat. Why does this happen? We've all been there, right? You find this grainy, low-res photo, you feed it into some AI tool hoping for a miracle, and what you get back looks like it was sculpted out of wax. Sure, it's clean, but it's lost all the texture, all the life. It's just off.
Well, the reason this happens all comes down to a concept called inverse problems. And that's just a fancy term for having to work backward. Think about it. When a photo gets blurry, information is literally lost forever. So deblurring means you have to guess what that lost information was. It's the same thing for adding color to a black and white picture or filling in a big missing chunk of an image. You're trying to undo a process without knowing all the original detail.
And this slide, this is perfect. It shows the two completely different ways AI can approach this problem. The old method, on the left, that's kind of like a police sketch artist who interviews 10 different witnesses and then tries to average all their descriptions into one single face. What do you get? A blurry, generic blob that doesn't really look like anyone. It's a mathematical average, sure, but it's not a real face. The new method is like that same artist drawing 10 totally distinct, sharp, and realistic faces, where any one of them could be the right person.
This brings us to a huge, fundamental conflict right at the heart of image restoration. You see, there's this massive trade-off between what looks real to our human eyes and what is technically, mathematically accurate. It's actually got a name: the perception distortion trade-off. Now, distortion in this context just means the mathematical error, like how far off the pixels are from some perfect calculated answer. And perception is exactly what it sounds like: how good, how sharp, how real the image looks to you and me. The big problem is you really can't have it all. You can't max out both of these at the same time. And hey, this isn't just an idea. It's a proven principle in this field. As the researchers Blau and Michael Lawley put it so perfectly in their 2017 paper, when you're doing this stuff, one always improves at the expense of the other. It is a constant, unavoidable tug of war.
And this graph shows you those two extremes in action. On the left, you've got the old school methods. They focused on minimizing something called the mean squared error, or MMSE. Basically, their goal was to get the lowest possible mathematical error. And they did, but the results looked awful, super blurry and totally fake. Then you look at the new diffusion models on the right. They go all in on perception. They are aiming for an image that looks absolutely perfect to us, even if it means the math isn't quite as precise.
So, what is this new way, then? How does it work? Well, it all comes down to this really radical shift in thinking. It's about moving away from finding one single answer and instead embracing all the possibilities. So just to recap the old way, it was always a mouth problem. The goal was to calculate the conditional expectation, which is really just a fancy way of saying the average of every single possible outcome. It's trying to find that one single most probable image. And like we saw with our police sketch artist, the average of all possible faces doesn't look like any real person. It's blurry because real faces have sharp, specific features: wrinkles, pores, you name it. An average smooths all of that away. The technical term is that it falls off the manifold of real faces. You can just think of the manifolds as the exclusive club of all possible realistic-looking faces. That blurry averaged face, it just doesn't belong in there. The new way completely flips the script. It doesn't try to calculate a single average at all. Instead, it samples from what's called the posterior distribution. Now, don't worry about the term. In simple language, it just looks at the blurry photo and asks a different question. What are all the possible, valid, sharp photos that could have ended up looking like this when they got blurry? And this is the magic right here. Instead of one blurry compromise, we get a whole bunch of different options. Each and every one is sharp, it's realistic, and it's a totally plausible explanation for the messed up image we started with. We get choices, not just one flawed final answer. Okay, so how does the AI actually do this? How does it come up with these different plausible realities? The mechanism behind it is actually surprisingly simple and elegant. It's basically a guidance system. So the AI starts with nothing but a canvas of random static, like an old TV with no signal. Then, over and over, hundreds of times, it applies two competing nudges. The first nudge is the diffusion model saying, hey, make this look more like a real photograph of a person. And the second nudge chimes in, okay, but also make sure it's consistent with that blurry photo you were given.
It just keeps repeating this delicate balancing act, and slowly but surely, a sharp, realistic image emerges from all that noise.
Now, this ability to generate multiple different options, it's not just some neat party trick. This represents a genuine revolution in what we can do with artificial intelligence.
What we're seeing here is a fundamental shift in perspective. We've moved from trying to find a single point, a single right answer, to exploring a whole cloud of solutions. And every single point in that cloud, every image the AI generates, is a completely valid, high-quality, potential reality.
And the applications for this are just incredible. I mean, look at this list. For super resolution, it means you could take one pixelated face and generate several different, distinct, high-res people that it could have been. For colorization, the AI could look at a black and white photo and show you that a hat could have been red or blue or green, and give you realistic versions of all three. It can fill in missing parts of a photo in countless believable ways. It's amazing.
But here's what I think is the most mind-blowing part of all of this. This gives us a genuine superpower that we have never had before. We can finally visualize and actually measure the AI's own uncertainty. So how do we do that? It's simple. We just compare all the different images in that cloud of solutions. If a certain spot, say a pixel on a person's cheek, is the exact same color in every single picture it generated, well, the AI is pretty certain about that. But what if the texture on a bedsheet or the precise expression in someone's eyes is changing wildly from one sample to the next? That's where the AI is uncertain. It's basically raising its hand and telling us, look, I know there was something here, but I'm having to guess at the fine details. And this brings us to one last really fascinating question to think about. The old AI gave us one single answer and insisted it was correct, even when it looked totally fake. This new AI gives us a whole cloud of possible truths, and all of them look real. So if an AI can show us not just one restored reality, but all of them, what does that do to our idea of what truth in an image even is? It's a pretty powerful thought to end on.